Okay, so we're looking at topic 4 today in mechanical systems. We're going to look at force, pressure, and area. So just review, we did look at pressure in our very first unit. So the force F acting over a certain area, so capital A, it is called pressure, shown as P. Force is measured in newtons, area is measured in meters squared, and the unit for pressure becomes newtons per meter squared, but that unit is also called pascals. So 1 kilopascal is equal to 1,000 pascals. So this is our formula for pressure. Pressure is equal to force divided by area. We can rearrange the formula to solve for for example, force. If we're solving for force, it becomes pressure times area. If we're solving for area, it becomes force divided by the pressure. This is just showing, you've probably seen this sometimes, maybe in magic shows or whatever. A person can lie down on a bed of nails and not injure themselves. Now compare that to stepping on or lying down on a single nail, right? Which one would hurt more? It would be if you stepped on or were lying down on a single nail, because when we're looking at a bed of nails, the force of the man's weight is being spread out over a larger area. So there might be a little bit of poking from the nails, but it wouldn't be life-threatening. All right, so that leads us to Pascal's law. Pascal's law, which we've covered before, so this would be review again, it states that pressure exerted on a contained fluid, so in a closed system, that pressure is transmitted undiminished in all directions throughout the fluid and perpendicular to the walls of the container. So there's many mechanical systems and devices that use Pascal's law. So a hydraulic lift, for example, it's a mechanical system that raises heavy objects, such as a vehicle on a service station lift. Keep in mind it is in a closed system, so it's using a fluid under pressure in a closed system. So it's a self-contained collection of parts. Another example of a closed system is our human circulatory system. Our heart, it pumps blood to all of the cells of our body and then back to the heart by blood vessels that are directly connected to one another. So that's another example of a closed system. All right, so a hydraulic lift, it consists of a small cylinder and a large cylinder, and they're connected together by a pipe. And usually each cylinder is filled with a hydraulic fluid. It's usually oil. Water is generally not used in a hydraulic lift, usually because it's not a very good lubricant and it can cause parts of a system to rust. So it's usually an oil that is used. And then each cylinder, it has a piston shown here that rests on the surface of the oil. Okay, so piston, the pipe in between, cylinder, pipe in between, and then the pistons are on top, resting on top of the fluid. All right, this is an example of a hydraulically powered device. This is a forklift that is used to move very large containers. All right, so let's say we are applying a force of 500 newtons to the small piston, and the small piston has an area of 5 centimeters squared. Therefore, the pressure will be 100 newtons per centimeter squared, which is the same thing as 100 pascals. So here is how we've done that. So here we have 100 newtons per centimeter squared, and so keep in mind the smaller piston here, or the smaller cylinder, had an area of 5 centimeters squared. And Pascal's law states that the pressure is going to be unchanged. It's going to be transmitted unchanged through the liquid. So therefore, the pressure in the large piston will also have a pressure of 100 Newton centimeters squared applied to it. All right, but the total area of the large piston is greater than the area of the small piston. So the large piston's area, let's say, is 50 centimeters squared. It's given to us. So the total force on the large piston will be 100 Newton centimeters squared times 50 centimeters squared. So the upward force on the larger piston is 5,000 newtons. All right, compare that to pressing down with 500 newtons of force on a small piston. So pressing down 500 newtons, we have a pressure of 100 newtons per centimeter squared throughout the system, and that will push up with an upward force 5,000 newtons. All right, so hydraulic lift, it uses a liquid to produce a large force on a load when a small effort force is exerted on the liquid. So that's what we saw in that example. So because a small effort force produces a large force on a load, there is a mechanical advantage for a hydraulic lift. And we can calculate that. We'll take a look at Pascal's law of mechanical advantage. So here we're looking at a simplified diagram of a hydraulic lift. So here we have a small piston, which is just 1 unit. So if you're pushing down on the piston with a force of 10 newtons, we're going to have a pressure in the fluid by 10 newtons per unit of area. So now if we look on the other end, we have a larger piston. It has 9 squares, 1, 2, 3, 4, 5, 6, 7, 8, 9, compared to the only 1 square here. So therefore, each square has the same area as the small piston. So according to Pascal's law, the pressure on every unit of area of that piston will be 10 newtons. And because there's 9 of them here, we will go 10 times 9, so therefore 90 newtons. Okay, so that is the total force on the large piston. All right, so looking at mechanical advantage next. So we exerted 10 newtons of effort force, and that caused the large piston to exert 90 newtons of force on a load. So there is a mechanical advantage, and we can calculate that by taking our load force, dividing it by the effort force. So our load force here was 90 newtons. Our effort force was only 10 newtons. So that gives us a mechanical advantage of 9. Meaning you'd have to push the piston 9 times farther than the distance you could lift the load. So you'd have to increase the work. You'd have to increase the effort distance because the work done on the small piston has to be at least as great as the work done on the load. Okay, so it's going to... Okay, next example here. You want to lift a 90 Newton load a distance of 2 meters using the hydraulic lift. Approximately how far would you have to push the piston as you exert your effort force? So the first thing we'll do is calculate the work done. Work is force times distance, and that work effort is equal to the work of the load. So 90 newtons times 2 meters, that gives me 180 joules of work. Okay, so next we're trying to calculate distance. So we know that work is equals to force times distance. So to calculate distance, just divide by force on both sides. And that tells me that distance is equal to work divided by force. Our work was 180 joules. Our force is 10 newtons. So dividing that will give us our distance. Our distance is 18 meters. So therefore, to lift a 90 Newton load, a distance of 2 meters using the hydraulic lift, we would have to push the piston 18 meters. Okay, this effort distance is 9 times the load distance. Here we're just taking a look at how we can set it up as a ratio. So in this diagram, we have a small piston. The mass is 40 kilograms, and the area of the small piston is 0.5 meters squared. And here's our large piston. The mass on it is 1200 kilograms. What is the area of the large piston? So we can set up our ratio here. So 12 kilograms is equal to large area, or X, that's what we're trying to figure out. 40 kilograms is equal to 0.5 meters squared. So it's set up like a ratio, and now we just have to solve for large area. So you can do that with cross multiplication. So you multiply the two numbers that are diagonal, and then divide by 40 kilograms. Okay, so not quite shown there, but what we are doing is we're doing 1200 multiplied by 0.5, and then we are dividing by 40. And that will give us our large area, which is equal to 15 meters squared. All right, so I'm just going to pause here. Okay, so this lesson, we're just doing a quick review of Pascal's law. Basically, Pascal's law, if you apply pressure to fluids that are confined, meaning they're in a closed system, they can't flow anywhere out of this system, the fluids will transmit that same pressure in all directions, and the fluids are incompressible. So this is our closed system. It's a hydraulic system. And so in this particular example, this is question 4 in the worksheet, Pascal's law. The small piston, it has an area of 10 centimeters squared. The large piston has an area of 75 centimeters squared. The pressure on the small piston is 300 newtons. So we're pushing down on this with 300 newtons. I'm just going to add that onto the diagram. 300 newtons there. And we have to calculate the pressure. So pressure is equal to force divided by area. Okay, so force is 300 newtons, and the area is 10 centimeters squared. So the pressure in this case is 30 newtons per centimeter squared. Okay, that is the pressure. If it was in meters squared, then we could put this into pascals, but that's okay. We'll just leave it as newtons per centimeter squared. So therefore, if that's the pressure when we push down on the small piston, what's the pressure applied to the large piston? So because of Pascal's law, it says that it's going to be the same pressure in all directions. So therefore, the pressure is still 30 newtons per centimeters squared. All right, the pressure doesn't change. Now we have to calculate the force that's going to push up on that large piston. All right, so when we do that, we have to rearrange our formula for pressure. So we know that pressure is equal to force divided by area, but now we're solving for force. So force is equal to pressure times area. All right, so force will be equal to a pressure of 30 newtons per centimeter squared, and it's multiplied by the area, which was, if we go back to our diagram, it is 75 centimeters squared. So 30 times 75, we'll put that into our calculator. 30 times 75, 2,250 newtons. Okay, so going back to what we've just learned, in this particular instance, if you push down with 300 newtons of force on a small piston that has an area of 10 centimeters squared, we are going to get a force pushing up with a force of 2,250 newtons when the area is 75 centimeters squared. All right, so the pressure stays the same. The pressure doesn't change. That's what Pascal's law tells us, but the force increases on that larger piston.